I am back to bother you with more dry math for another 40 minutes, but this will also be a short session. Okay, so last talk, well, this is the outline for this talk, but we'll go through it. So here's a quick summary of what we spoke last time. All of this dealt with continuous functions, but people don't use pen and papers anymore, which is where continuous functions are most useful. And nowadays, we all work on our laptops or on computers, where everything needs to be digital. And digital, by definition, means that you don't have infinite time, and plus you don't have a continuous time domain. You have a discrete time domain. So the first thing we'll talk about is sampling, or how to discretize a continuous function. So here is the sine wave that we started off last talk with. This has a frequency of 2 Hertz. So there are 2 oscillations every 1 second. What happens if I sample this at 2 Hertz? I pick one point on the sinusoid every time it oscillates back and forth. But if I do this, I will end up with a straight line, which you can get by just drawing a straight line through all these orange points. So sampling a sinusoidal function at the same frequency as the sinusoid will not help us reconstruct it. If I go to double the frequency and know for a fact that it's a sinusoidal function, we can reconstruct the frequency, because now I know it has to go through a positive cycle and a negative cycle within this period of time. If I sample it at greater than twice the frequency, then I have enough points to reconstruct the entire sine wave. So if you have any function, any periodic function, we said, can be decomposed into its respective frequency components, you identify the fastest frequency, and then you sample at twice that fastest frequency to reconstruct your signal completely. And this is called the Nyquist sampling theorem, the other theorem Nyquist came up with, along with many things he did. And this is a very important result, or this is a very important concept to know. You will be sampling functions all the time when you do digital signal processing. And if you sample at less than twice the maximum frequency, you will face a lot of problems in reconstructing your time domain signal. So the next important question is, I have a discretized time domain signal. How do I Fourier transform it, and what happens to the Fourier transform? This process is called the discrete time Fourier transform, or DTFT for short, one of the many jargony terms we're going to see. The discrete time Fourier transform is, in formula, just the Fourier transform equation where the integral goes back to the summation over a finite number of points, n, but here n runs from -infinity to infinity because we don't know what's the length of the time domain signal. So if I take the sine wave, and that is Nyquist sampled at 5 Hertz, I reconstruct back the 2 delta functions of that sine wave that we saw even in the continuous case. So all is well and good. We can Fourier transform a sampled function as long as it's Nyquist sampled. To see the bigger picture of what the DTFT is doing, we need to zoom out of and see the bigger frequency range. So if I increase this frequency range from -44 to -7 or -8, you can see that what happened in the frequency domain is that the 2 delta functions that is actually the Fourier transform of sine wave has been replicated over and over again. And the replication happens at the sampling frequency over 2. And this is a very, very important result, which will be useful later on in numerous ways. If I increase the sampling frequency to about 10 megahertz, the original frequency remains the same, so my delta functions are in the same location. But since the sampling frequency has changed, my replication happens at a distance further away from each other than before. This is true for aperiodic signals as well, not just periodic signals. So this discrete function becomes a continuous function if I sample a Gaussian. But the replication in the frequency domain will just give me multiple Gaussians instead of a single Gaussian function. Again, replicated every fs by 2. These values are just the values I got for this corresponding graph. So the DTFT of a Gaussian is not a Gaussian anymore, but a sum of Gaussians centered at different frequencies. So far, so good. Also note that this is at 0. This Gaussian is centered at 0. This Gaussian is centered at the sampling frequency fs. The next one will be centered at 2 times the sampling frequency, and so forth. What happens if you One way of looking at the sampling, or what happens when you sample here, is you are taking the original function that you have and multiplying it by a Dirac comb. So I have taken a continuous function and multiplied it by the Dirac delta function, or a train of it, to sample it. So what happens correspondingly in the frequency domain is you get a convolution of the same Gaussian with the Dirac comb. And convolution is not multiplication, it just results in the Gaussian being replicated multiple times. And we said there is an inverse relationship between the width of the Dirac function here and the width of the Dirac delta here. So here, if my samples are very closely spaced to each other, my Gaussians are replicated very far from each other, which is again determined by the sampling frequency as well. So higher the sampling frequency, the wider the distance between these Gaussians. The smaller the sampling frequency here, the shorter the distance between the replicated Gaussians in this case. To the point where if I don't Nyquist sample it and undersample it, what happens is my Gaussians are squished together and I lose information. And this problem is called aliasing. And this is what will happen if you undersample your signal. So in a lot of cases in radio astronomy, how we get around this is by band limiting the frequency domain. So Dan explained one reason why you want a band limit, which is in interferometry to recover the fringe. Another reason why you want a band limit is because then you can, if you restrict the frequency ranges in which your signal is going to be, you know definitely what twice the maximum frequency would be, and then you can Nyquist sample it. But undersampling is not always a bad thing. Aliasing sometimes is done intentionally. This relates to Nyquist zones. So because of the Nyquist sampling theorem, the region between 0 to fs by 2 is called Nyquist zone 1, Nyquist window 1. The region between fs by 2 and fs is called Nyquist zone 2. The only difference between these Nyquist zones is all odd Nyquist zones have the spectrum as it is, and in the even zones, the spectrum is reversed. In the case of a Gaussian, this is a little hard to see because this is a symmetric function. But if you have had an asymmetric function, like if we go back to the sine case, you can, in the Nyquist zone 2, which I don't have there, it will be flipped. It will be inverted. So sometimes what we do in radio astronomy is if we know that the signal you want to measure is very tiny, like say, for example, the hydrogen spectrum from the galaxy occurs at 1.4 gigahertz, but it's a very narrow signal, and maybe you want to measure only 10 megahertz around it or 50 megahertz around it, but it's at gigahertz. So if you want to go by the original Nyquist criterion, you probably have to sample it at double that, so which is 3 gigahertz or maybe 4 gigahertz, which is a high sampling frequency. But you know that you want to measure only 50 megahertz around that region. So what you can do is you band limit. First, you put in a filter, which will filter only 50 megahertz over that window. And then you can either down convert it by multiplying it by a cosine, which we saw in the last Fourier transform talk. Or you could just undersample it intentionally. It will fall under a Nyquist window that is much higher up. Maybe it'll be the 4th Nyquist window or a higher up signal. But it will get down converted naturally because you're undersampling. That trick is used sometimes, but has to be used with care, because the analog electronics that you're using and the digital electronics you're using should still be able to accommodate that high frequency before you have digitized it and before you have undersampled it. So you should make sure your analog beam width can still accommodate that. But if it can, you can just use Nyquist undersampling to down convert your signal all in one step. Any questions on that? Okay. So what happens if you sample in the frequency domain? If I sample my frequency domain, because again, in digital electronics, your frequency domain is also discrete, is not continuous, it results in periodically repeating the time domain. And this is also, again, a direct result of the Dirac delta comb. If I multiply in the frequency domain, it's a convolution in the time domain. So this results in a convolution with the Dirac delta function. And the exact same thing that happened from going from time to frequency happens if you go from frequency to time. And so to put it all together, what happens is if you have a discrete time domain, or a sample time domain, and if you want a sample frequency domain, you end up replicating both the time domain and the frequency domain at certain intervals. As a summary, the continuous to continuous case is the continuous Fourier transform, which we saw in the last section. Going from a discrete time domain to the frequency domain ends up replicating the frequency domain because you've convolved with the Dirac-Delta function. If you have a continuous signal, if you have a periodic signal in the time domain, the frequency domain will be discrete, which was the original Fourier series that we had seen, and we just inverted back to that conclusion again just now. And if you have both discrete, they're both periodic in functions. And this is kind of the overall Fourier transform slide that you would ever want to know without any equations. So the discrete Fourier transform, or the DFT, is what you most often see in digital signal processing. You don't see Fourier transforms, you don't see DTFT that much as well, but you see a lot of discrete Fourier transform. The equations for the discrete Fourier transform are very similar to the Fourier transform, only the integral goes back to summations. But the summation doesn't run from -infinity to infinity, most importantly, because in digital electronics, you have to time limit and band limit your signals because you're dealing with finite length signals in both cases. And I will come back to why the summation runs from 0 to n and why the summation is the same in both cases. So some properties of DFT. The properties of DFT very parallel the properties of Fourier transforms a lot. One of them is linearity. Here you can add signals and you get the addition of their Fourier transforms. But one important thing which is not true in the case of Fourier transforms is these are both periodic, as we saw. And this periodicity is very useful and sometimes is not that useful and is harmful, and you should take care of it. But you should remember that it is n periodic over that factor n. So a shift in the time domain results in multiplying it with an exponential signal in the frequency domain, like it did in the last case. But here, this is accounting for the fact that it is periodic. So if it is not periodic, this exponent would have been a lot more complicated, but it gets simplified and analogous to the FT because it's a periodic shift. In the case of the frequency domain, this also becomes a periodic shift. So you are shifting the Gaussian, in the case of the Gaussian, and it loops back and comes around on the other side of your signal. A conjugation in time results in a flip of the Fourier domain and a conjugation, which is a useful property you can use sometimes. The time and frequency reversal is a very important property. If you reverse your time domain, you reverse your frequency domain as well, and they're reflections of each other. This is also a function of the periodicity and not in general true for Fourier transforms. Symmetry that we saw in Fourier transforms still exists here. If you have a real and even function, you still get a real and even function. A real and odd function will return an imaginary and odd function. Convolution, the convolution theorem still holds, but it becomes a circular convolution where y then starts getting reversed on its axis. And especially in this case, you have to take care of the fact that these are periodic functions. Because if you want to convolve a function with another function, the convolution will not account for the fact that you don't want an overlap in some situations. So going back to the analogy of having the f of t and g of t equations, when you flip them and overlap them, a lot of that portion was 0 in the continuous case, but it will not be 0 here, and they will overlap with each other. So you have to account for this fact and take care of it, which we will see one way of doing later on. The correlation theorem is also the circular equivalent here, but the product will still be the same. Caveat the fact that you have to take care of unnecessary products when you're circularly correlating it. One important similarity between in the DFT is that there is a relationship between the samples and the sampling rate in the time domain and the samples and the sampling rate in the frequency domain. So if you first look just at the graphs, this is a signal of period t naught, and this is and sampled at time period t. 1 over t, which is the sampling frequency, determines the length of the Fourier in the Fourier domain, which is here fixed as Fs. So T is related to Fs in this relationship. Inversely, if you sample the frequency domain, we said it results in periodicity in the time domain, and this capital F, which is the sampling frequency in the frequency domain, becomes a time period, which is T naught. But what these two equations do for us is they make sure that the number of samples in a given period in the time domain is exactly equal to the number of samples in a given band in the frequency domain. And both of them reduce to the same value n, which is why in the discrete Fourier transform equation, they both run from the same summation n equals 0 to the same capital N, which is the number of samples. One useful, there are multiple places where this relationship will be useful. Like, for example, if you want to increase the resolution in your frequency domain, you have to, is it sufficient if you increase the sampling rate in your time domain? So if you want to increase the resolution in the frequency domain, what would you do to your time signal? You need to expand it. So increasing the sampling rate in the time domain will not increase your frequency resolution. Extending the length of time in your time domain will increase the resolution in your frequency domain. And this was at least counterintuitive to me when I first started. So you have to increase the length of time to increase the resolution. And in this case, you want to increase the bandwidth to increase the resolution in your time domain. So the length of the time domain is the frequency resolution, and the resolution in the time domain is the bandwidth that you can measure of your signal. So one way artificially of increasing the resolution is by something called zero padding. What you do is you have a periodic function, but you want to increase the number of points in your frequency domain. What you do is you just take the aperiodic signal that you have and pad it with a bunch of zeros, and you've artificially improved the resolution in your frequency domain. This is both useful and dangerous. It's useful because, for example, when you're doing a circular convolution, all the zero padding will avoid the unnecessary products that we were talking about. And this is sometimes required, not just useful, but it is required, especially when you want to use Fourier transforms to compute your convolutions instead of the other way around. So, and another case in which zero padding is very useful is to make capital N a power of 2. And we will talk about why we want to make it a power of 2. That is because you want to use the fast Fourier transform algorithm to compute your discrete Fourier transform. But it doesn't help in a lot of situations. For example, if your signal is aliased to begin with, and this Gaussian has not been sampled at the sampling rate required, the zero padding will not improve your frequency spectrum at all. So this, for example, does not help with aliasing. And in some cases, it also doesn't improve the signal to noise in your frequency domain. So zero padding is useful, but it's tricky to remember that it is sometimes completely useless. So what's the fast Fourier transform? This is the last section of the talk. The fast Fourier transform, which is the most common usage for a Fourier transform. Everyone just says FFTs now. No one says FT. The fast Fourier transform is an algorithm to solve the discrete Fourier transform. It's an algorithm that Cooley and Tukey came up with, I don't know back when, really, that makes the FFT, that computes the DFT in n log n time instead of n squared time. So the DFT equation, if you go back here, involves a bunch of complex multiplies and a bunch of complex adds. More specifically, to compute every k value, so let's say I fix the value of k to 0, I have to make n multiplications, or n minus 1 multiplications, and n additions. So that is n operations to compute every single k. And there are n k's. So to compute n number of k's, I have to do n times n, which is order n square operations, which can become very, very expensive if the n value is in thousands. And even now, actually, we very frequently do 1024-point FFTs, which would be incredibly complex if you try to compute the discrete Fourier transform in this fashion. So the algorithm Cooley and Tukey came up with was getting insight into the periodicity in the DFT formula. And I have no better way of explaining it other than like to mathematically go through the derivation. So I will try to do that in as direct a way as possible. So the first thing we will do is call this exponential function right here, which keeps coming up again and again, a Wn, because it'll then be easier to write. So this exponent that keeps coming up in DFT, which has a k and n on top, will just become Wn to the power of kn. This is called a twiddle factor. Useful things about the twiddle factor: if you have Wn n squared, it is equivalent to writing Wn by 2, which you can very easily see by taking n by 2 and removing the 2 there. Wn at half the period is just -1. So what I will do to the discrete, so this is the discrete Fourier transform if I just write the exponential in terms of this Wkn, and the summation still runs this way. The first thing I will do is call decimation in time in technical terms, but what it really means is just taking this xn and using this real, not coefficients, the real numbered values of x separate from the odd numbered values of x. This is just the numbering of the samples, not a fact of being even or odd or anything. This is just how you would number x. So the even numbered samples of x, you can see here, will just result in n being even. So I took out that 2 common and wrote down n, and now n doesn't run all the way to capital N, but runs only till capital N by 2. So I have halved this summation basically here, and the rest of the half is right here, which is all the odd numbered values. In this, what I will do is take out this k, this 1 times k outside, because it doesn't involve a small n, so it doesn't need to be inside the summation. And now this and this look exactly similar. Also, I have taken this W squared n and used the similarity right here to write Wn by 2. And now you can see that these two summations in themselves, which are half of the total summation required to get this, are exactly same as this. So this is like a DFT, like a discrete Fourier transform, but over half the number of samples x the entire length x has. And this is the rest of the half. Now the brilliance in the FFT algorithm is seeing that these two can be computed in an easier way. So if I call this entire even part of the summation f and the odd part g, you can see that f and g are both n by 2 periodic in themselves. Since they're both discrete Fourier transforms, they're both periodic, and they're periodic with the periodicity that is half that of the original signal, which then makes xk, which is the value that we want to compute, periodic over n by 2. Sorry, it doesn't make it periodic, but the second half is just the subtracting off this product from f of k. The first half of xk, the first half of the Fourier transform, is if you add these two things, and the second half is just subtracting these two things. So what I have done in observing this pattern is I have halved the number of multiplies I need to make. So I don't need to make n multiplies for computing every point on my Fourier transform, but I only need to compute n by 2 multiplies now. And once I come down to the next step, I can do half of even those multiplies. So this changes the algorithm from being n squared to being n log n.
You have about 10 minutes.
This is my last slide. So every FFT can be decomposed into the even samples and the odd samples. And if I can do an n by 2 point DFT on the even samples and another n by 2 point DFT on my odd samples, I can reconstruct the Fourier transform again with half the number of multiplies. And this can use the same algorithm again to compute half the number of multiplies and so forth, and propagate all the way down till I just have the even samples here and the odd samples here. And this algorithm, the FFT algorithm, is what we widely use today and is written in numerous languages. There are multiple C versions of it. There's a Python version of it. There's a Fortran version of it. And there are multiple versions within each language which will help you use this algorithm or algorithms that are better than this. One of the many unsolved problems in computer science is reducing the complexity even more. It's not capped that it should be n log n. So if any computer science students here can come up with an algorithm that scales only as order n, you will be instantaneously famous. And that's the last slide of my talk. Thank you.